So this morning and afternoon, I intend to work on this chapter, which is called a little bit different from the PDF, but it's the same as what Cécile and Milita sent you. It's basically starting to introduce vocabulary about source-to-sink, how source-to-sink systems are composed of different subsystems, and what are the dominant processes that play a role within those subsystems. And this is 3.1 and 3.2 from source-to-sink, the succession of three subsystems and major processes and controls. I don't have a precise timing. That's not a good thing, but I didn't time really well this aspect. So maybe we will be late, maybe we will be early. But the major processes, I think, will be important for this afternoon when you will start practicing with models. Okay, and again, like we said yesterday, do not hesitate to just stop. You know, I like to talk, so maybe I'm talking too much. So just say, Sébastien, even if I'm speaking, don't hesitate to interrupt. It's a course, so it's okay. Because since I'm on my small screen, I really need to. I don't see people, in fact. So I don't know if there is a hand raised. Maybe I don't see it. So don't hesitate. Okay, so I just wanted to start. Sometimes I like to start with some procrastination and digression. And I really like this book by Gaston Bachelard, who is a French philosopher. Because it's about philosophy of science. It's going to be a short digression, and it's all in French anyway, so I won't stay long. But in this book, and I can only encourage you to read broadly, not only scientific papers about your own topic, but really broadly. In this book, I really like what he says. This is beginning of the 20th century. And, you know, this sentence here is saying that normally we already find answer by linking signs, observations, not only numbers. So I think it's important because we need to be quantitative, as I said yesterday. So that's important to be quantitative. But we should always also consider what is named here qualité. So not only quantity, but also quality. So the character of observations can also be used. You know, even if you do not describe them as numbers, sometimes when you link observations together, you don't have numbers necessarily to link them. You may find original numbers to link them, but sometimes it's also important to link those qualities. And sometimes it's actually the first step is to link observations together, and then you start quantifying. But both should go together. So I just think it's good to sometimes refer to those ways. This comes from a completely different view of science. It's not geology, but it's sometimes interesting to look at other sciences. Okay, so I will start. This is one slide, but we could stay very long on it. I will start with a very conceptual, very simplified view of the source area. That's also because we don't really know, each one of you, what are your knowledge on those things, but this is some vocabulary. And vocabulary is really fundamental. You know, behind the word drainage area each of you should have an image, an object, because that's our common language. So vocabulary is fundamental. Even if, I mean, that's basically the way we have to describe and communicate. So it's fundamental, in fact. The more vocabulary you have, the more you can speak about those objects and your topic. And we can discover new words every day. So here I just simplified the source, and I have also a little bit of a potential sink or transfer system here. But as you can see, I have a trust here. It's supposed to be a 3D diagram. I don't see if I don't know if you see it as me, but I draw that. There is a section here through the landscape. Here is a fault at depth, trust fault, and here is the surface with the little triangles. Everybody knows this is the block going up, the hanging wall, and this is the block not moving, which is called the footwall of this system. There is no real scale, but this could be, a block in the Basin and Range or in the Apennines where Alex Whitaker was working. So that could be 10, 20 kilometers wide. It could also be, the Pyrenees, for instance, also 25, 50 kilometers wide. So it's kilometric scale. And so here I really simplified, but the drainage area is this of there. Here we see one drainage area, one that's also called a catchment or a drainage basin. Okay. And so all of the rainfall that comes here is trapped in this area and is collected into this river system. Okay. And all of the water goes out here at what is called the outlet of the basin. You see, I've put basin outlet here. So here we can see one basin, a second basin. Here, this is half of a basin because there is only half of it, and that's the longitudinal profile of the river. But so at the basin outlet, my discharge, the water discharge coming here is the discharge that results from collecting water in the drainage area. We have here the range, the mountain divide. You know, this is this line here. So every drop of water coming on that side will end up on this side of the mountain. If it goes on the other side of the divide, it will go the other way. But divide is a term that you can also use for the divide between these two valleys here. You know, there is a divide virtually in every separating every drainage basin. So there is the mountain range, the main divide, but there are also a lot of divides, local divides that separate each drainage areas. And here I have put a main stream. So I only represent a main stream with hill slopes on the side. We can say also interfluve, the whole area between the streams. But if we would zoom in into this valley side here, maybe we would see little streams. Okay, so there is a whole network of streams with a main stream and tributary streams, you know, like these ones here that I've represented here and that I will speak about afterwards. Okay. A real hill slope is an area of the land in the drainage basin which has no channels on it. So it's where you can walk basically, where the cows are also walking, where the animals, where vegetation is growing. So this is really where there is no channels, no little streams in it, a hill slope. And the processes on hill slopes, the processes of sediment transport, are different from the processes in the channels, okay, in the streams. On hill slopes, processes are more distributive in general of the sediment. So the sediment, the rocks, they move a bit together slowly. There can be a lot of different processes moving sediments on hill slopes. It can be often it's just gravity. So the sediment, they go downhill just because of their own weight. You have all of the weathering processes happening on hill slopes. Water goes in, ice, cold, heat, vegetation. All of these are processes that destroy the rocks on the hill slopes and transform them. Little animals, you know, they do an incredible job in moving sediment. And because there is a slope, most of the sediment that goes down, thanks to animals, does not go up anymore. So progressively, this adds up and make a downslope motion of the sediments. One big process is also landslides. You know, it's here on the hill slope. I just represented a scour, and there's a whole mass of the hill slope that went down into the mainstream. Okay. I can point you to many papers studying how processes act on hill slopes. What's important is to know the rates of processes acting on hill slopes and how they can react, and to what they can react, to what environmental factors they can react, if you want to understand how they deliver sediment to the river system. The other thing to notice is that 90% of the land surface in the source is hill slopes, and only 10% about is channelized in the form of streams. Okay, so the drainage network, the fluvial network, is often only 10%. Of course, this varies, you know, the drainage, we speak about drainage density. You can have a densely drained landscape with a lot of rivers, and a landscape which is dominated by, much more dominated by hill slopes. And these are things we can test easily with numerical models. But in general, anyway, the hill slope dominate the surface. Okay, do you have questions at that point? If no, then I just continue a little bit.
No, all good, I guess.
Yes, Lucas?
No, just saying that.
Thank you. Thank you. Here you see a longitudinal profile. We call that the longitudinal profile of the river. And I represented one knick point. You know, it's an inflection. Actually, it's an increase in slope downstream, which is local. I have also represented the terrace. The picture is very small, but here you are on the left side of the river. You know, we always say left. We always speak downstream. So this is the left side of the river, and there is a terrace. So there is a little rise and then a flat surface here. So these can be different things, but often it's the ancient riverbed that has been abandoned. Okay. Here I already wrote something is concave bedrock river profile. So concave is this shape. I know this is trivial, but it's good to agree on the terms. So it's this, the slope is decreasing downstream. That's a concave profile. And bedrock would mean that if you go in this river with your boots and you look at the bottom at the riverbed, you see the bedrock. So your riverbed is not completely covered by moving sediments. You know those streams in the mountains where you can you can see the granitic bedrock. It can be also a sedimentary bedrock, okay? But the riverbed is actually almost clean. There is always a bit of sediment, of course, because when the river is not active, then there is the gravels there, but it's not completely covered. There's a lot of discussion on how to characterize the river profile, the riverbed. but it's a bedrock. In theory, a purely bedrock river profile would be a clean bedrock profile, and you will see the basement. Often we are on mixed riverbeds, so the normality is that you see the bedrock in places and you see also sediment. But here, for instance, as another end member, here you are in potentially a sedimentary basin, you know, at the bottom of the river. So there is the source and the sink. And here, clearly, if you walk on this riverbed, you are on an alluvial riverbed. And that's an alluvial river profile. It's also much more linear. So here I'm describing the slope. The slope does not change much. It decreases downstream, but much slower than in the mountain. So it's mostly linear, or many of the segments of these river profiles are actually linear. And so here, if you walk, you can, you know, take a shovel, and if you shovel the bottom of the river, you will shovel sediments. Okay, so that's an alluvial river profile, an alluvial river, you can also say. And you see here, my bedrock river is in a valley. It's clearly incising, eroding. And my alluvial river here is actually in a floodplain. So the landscape is flat here, whereas here it's incised. Okay, so this is an erosive landscape, and this is a sedimentary landscape. We see the channels in section, but every time the channel, the river floats, it puts sediment on the side, and integrated over time, I'm just covering this area with sediment. This map, discharge and water levels in Switzerland, but it's the current situation, so it's perhaps different from what you find. I don't know if you see the map I'm showing. Somebody say yes or no?
Yes.
Okay. So here is the Rhône River. It's going all the way down here, here. It goes now northwards and enters Lake Geneva here. So here you have a that's not where I clicked. Here you have a hydro station. Also not, I think. Should be more. It is Rhône Porte du Sex 2009. That's the name of the station. And at the moment, cubic meter per second at the moment is 151. It peaked at 218 yesterday at 11. So it changes quite a lot. But these are hydrological data, you know. Ariel, for instance, do Prado in Bern is going to use that a lot. There are gauging stations, which are available in many countries and give you those kind of data. So I think it's a really a good help to have those data. Okay. So let's take the values. You know, I think we double checked with what Marine and others have found here, that probably the average on the century of 187 is a good average, because here we see this cubic meter per second, you know, 165, 93 here, much less, twice less than what we found on the century in the literature, but still it's oscillating. So I think the average that was found is good. Now, my next question was, so I want to use a little bit of these equations. Can you transform this cubic meter per second in cubic meter per year to have something annual? And let's see what you found. Don't hesitate to ask questions on the way, but I think it's good if we do that. So you have two options. You use an internet conversion tool. That's the lazy option. But to have cubic meter per year, you can also multiply by 60 to have it in minutes, then multiply by 60 to have it in hours, then multiply by 24 to have it in days, and then multiply by 365 to have it in per year. Okay, and what you should find share. What you should find is this. So I multiply by 60, 60, 24, and 365. What you should find is this number. So 3, 3, 3. So let's say it's let's say it's, I would say it's I would write it like 5,900 millions of cubic meter per year. Do you have the same number?
Yeah, more or less.
Okay, or maybe 6,000, but so a cubic meter, you have to realize what it is and put it, imagine it in front of your eyes, a cubic meter of water. That's 1 ton also. So we have 500, we have about 6,000, let's make a gross average to 6,000 millions of those cubic meter per year. And that's quite an interesting unit to know of. With that, imagine you work in the ancient systems, and to some extent you did some paleohydraulics, for instance, that we will teach you as well at some point, and you have estimated this paleo discharge. One thing you do not know is the size of the drainage area, and you would like to estimate it. You have the discharge. If you know this equation here, oh, sorry, I don't see my mouse anymore. Well, it's here. You have this equation: discharge equals drainage area times runoff or precipitation. So, and you want to estimate the drainage area. What value for the precipitation would you take? Question to all. So, does anyone has a? I don't see. Are you chatting or sorry? I'm not, because I'm sharing. I don't see. More chat. Yes, Philemon said 1,000 millimeter per year for the precipitation. So that's a good number. Let's see afterwards. But let's take 1,000 millimeter per year. Now, how do you estimate drainage area of the Rhône, of this river?
If I
how to
check the topography, perhaps?
the area?
Well, we have the discharge.
You just have to divide the discharge by the...
You have drainage area times air, and we just said air is 1,000 millimeter per year.
So it will be
so we have to divide exactly Q water divided by air, and that will give us drainage area. So let's see how you do that, because you have some units to change, but it's not too difficult.
Yeah.
So 1000 millimeter per year is 1 meter per year. I had, so I'm still sharing, I did have 6,000 millions of cubic meter per year. I now divide this by 1 meter per year. I think you should all get 6,000 times 10 to the 6 meter square. So this is the, do you agree?
Yep.
Yes.
Yes.
Okay. How many kilometer square is this?
6,000.
Yes. So we have estimated the drainage area of the Rhone from the discharge that we took as a data. That's the real the only real data we have so far, to 6,000 kilometers square. Okay. With this 6,000, so we only took the data, then we made a full estimation for the runoff. We took 1,000 millimeter per year, but that's a good number for if you do models, for instance. And we end up with this. Now, what is the length of the Rhone River when you know that? Can you estimate it now? What will you use to estimate the length?
The proportion of 1.7 times a.
Exactly.
5.
So you have the equation L equals 1.7 A 0.5. So speed contest on the result. I'm sorry, I cannot offer a beer to the winner, but if we were in presence, I would. Or we can start counting how many beers, if that motivates people to quickly give answers. 5,100, I don't think so, Caroline. More something like this, yes, because yeah, no problem, no beer. So yeah, 6,000 square is 77. Okay, and I put 1.7 in front. How do I do that? Yeah, and I get 131. 131 kilometers. So now I would go, let's check on the map to see how this is. So can you guys go on Google Maps or on any maps you want, or find a map? And okay, I can pay Lucas. No, Luca is paying for everyone. Excellent. So I would ask you again, speed contest on, is this a good number? Is this a good estimation or not?
Yes.
I think it is, because if okay, Marine, it is short estimation. Philemon, you think? If I go maps, we're speaking about the main. So this is Lake Geneva. And we can see the Rhone River here. So I think maybe Benjamin can comment, but I think the divide is here. And
yeah, that's correct. Yeah.
Correct. So if I look at the scale and I put, what can I put on my screen to make a scale? I go from here, 1, 2, 3, 4, 5. I really find, I mean, just measuring, I really find 130 to be a very good estimation. We could measure that better, but with this being 20 kilometers, you know, you go 1 time 20, twice, 3 times. Okay. So Philemon is commenting 3, 4, 5, 6, and then another 10 or another 20. So it's actually pretty good. That's maybe chance. That maybe is chance because not all basins look like Hack's law. Sometimes they can deviate quite strongly. But it just says, I think that it's correct. It's more or less correct. We could measure that better, but I think it's correct. Again, we're speaking about the main stream, the main trunk stream. Okay, this was a good exercise. Don't hesitate afterwards if you didn't, if you still have questions. I just take this opportunity to show you this fascinating place here. This is a divide, so it's I mean, often, you know, administrative boundaries are also geographic boundaries, but this is every drop of a cloud coming on this side here goes into the Rhône, ends up into Lake Geneva, then crosses Lake Geneva and goes all the way to sunny Marseille. Whereas a poor drop that will fall, you know, on the wrong side of the divide would end up here in the Rhine system. So here at this place, this is really a crucial place for if you are a water droplet, because you can either end up in Marseille or you can go all the way. I am lost. I think all the way here in the Rhône, yeah, in this part of the Rhine system. Sorry, then end up into Constance, but it's also actually beautiful. And then you pass by. Not by Zurich, but you go straight, sorry, into the Constance lake, and then you follow the Rhine River, pass by beautiful vineyards, and end up actually here, right? So I think it's. Am I wrong for the Rhine? Where does the Rhine end up actually? I don't see the river course on this map. Or is this correct? On 4. Oh, I don't see my map. Yeah, it ends up there. Oh, here in the north. So this is really typical of a divide, and that's pretty important. Okay, now I was thinking about asking you if you would find any way to calculate the sediment flux, and you know, answer the question that Amanda asked yesterday about the filling time of Lake Geneva. So how would you know, we have this equation as well here for QS. How would you calculate sediment flux now that we have drainage area? Does anyone can say something?
Probably we'll have to look for the erosion rate and then use that equation.
Okay. So what's what number would you put for erosion rate, even if we didn't look at it?
Yeah, that's the problem. Wouldn't be easier to measure the sediment flux and then come up with an erosion rate?
We could, but actually the sediment flux is not so easy to measure. We haven't spoken about this, but there is the suspended load, there is the bed load. So Yeah.
Sorry, do we know the general lithology of the basin? Because maybe there's a general erosion rate for a specific lithology we could apply.
So this will be quite precise. We could, here I'm just asking kind of orders of magnitudes, you know, because of course you're right. There are different lithologies in the valley, in valleys, in all this upper Rhone valley. And so it's not easy to have general rules for the erosion rate of a certain type of lithology. We can either use one number that we make up, like we did for the precipitation rate. But I was just wanting to ask you, what do you think it could be? What's the typical erosion rate? No idea? Or ideas?
I think maybe dozens of centimeters a year could be a good rough estimate. Maybe a little less.
Yeah, I think it's important. It's important to so I'm speaking really average erosion rate. So so you can try to figure out yeah, Philemon and Everton, that these are good ideas, but I'm just asking about, you know, what's a typical erosion rate? What are the typical orders of magnitudes of erosion rates? And Lucas proposed dozens of centimeters, but in fact it's closer to millimeter per year. And I think it's very, I'm still sharing the screen. I think it's still, it's important to think about, let me write something, millimeter per year. That's the unit, and it's equivalent to kilometer per million year. Okay, 1 millimeter per year is equivalent to 1 kilometer per million year. So that's very important, I think, to always have in mind. Millimeter per year, kilometer per million year. And you see, with an erosion rate of 1 millimeter per year, you erode 1 kilometer in 1 million year. So let's say you could think that, okay, if you stop tectonics, a mountain range like the Alps is 2.5 or maybe 1.5 kilometer of elevation on average. And so you would need 1.5 million years to completely erode the Alps. Okay, that's without complications. But you know, Lucas, if we had dozens of centimeters, it means we would erode mountain ranges really, really fast. Too fast even for living mountain range even growing in the first place. So dozens of centimeters can happen in very specific place, in local places, you know, when there is a local incision by a river, that can happen. But when we speak about catchment average erosion rate, so when you average the erosion rate at the scale of an entire catchment, we are more on the orders of millimeter per year. So Aurora wrote, there is a study by Corsandi that suggests 0.44 millimeter per year for meandering rivers. But this is, Aurora, this is an erosion rate, or what is this? Why is it for meandering rivers? And is this for the Alps? I don't hear you, and I don't see anybody on my screen because
She wrote it's an erosion rate.
My mic was acting up, sorry.
Okay.
Yeah, it was a erosion rate, but it's a study case. I didn't actually read where it is, but it's not on the Alps, no. It's in Asia.
Okay, okay.
Yeah.
So Esteban came up with 0.32 at the scale of the European Alps, 0.58 in the Northwestern Alps. So that's very good. Let's stop here. You know, there are different methods, and I'm not going to enter that, but the scale, what's interesting here is we are speaking about 0.something millimeter per year. So the if you see my mouse, the little arrow here is 1,000, 2,000 times smaller than this arrow here, the rainfall. Okay, so the erosion rate is really, so it means you have a measure here of the efficiency of precipitation in eroding. So there is much more water than sediment coming out of the system, and the concentration is going to be really small. The concentration, the amount of sediment, if you look at the concentration of sediment into a river, is really small, is of the order of thousands or percents. Okay, and we see that because when we see a river, we see only a few centimeters of sediment at the bottom. You know, you have a 2 meters water depth, and you have a couple of maybe you have 20 centimeters at the bottom of sediment. So these are the typical scales. Now, if you take 0.58, let's take the high number, 0.58, and you multiply it by drainage area. What kind of sediment flux do you find? Speed context again, and then we will answer that and make a break. Is anybody finding the answer? So we're calculating QS. Drainage area, 6,000 times to the 6 meter square, multiplied by 0.32 millimeter per year, which is 0.0 will be 10 centimeter, 0 will be 1 centimeter, 0 will be 1 millimeter. So we are here 0. That's correct. Okay, 0.32, 0.32 times 10 x to the minus 3, 0.0032, that's correct, times 6,000 millions, and 3, and 3. So we have 192, so sorry, 1,900,900 and 200, no, sorry. I'm not seeing this. 1.9 10 to the 6.
1.92 million will be
1.1.
Yeah, 1.92 million, sorry. 1.92 times 10 to the 6. Exactly. So these are 1.92 million cubic meter per year. Everybody agrees?
Yep.
Okay. And free, yeah, why did we take 0.32? I don't know. I said, so okay, it's better. What Amanda gives is basically free. Let's take the highest number is 3.48 millions cubic meter per year. Okay, with that, how much time do you need to fill Lake Geneva? So here you need to do a Google search to know the volume of Lake Geneva. Do you all get that? Has everybody seen this this number, 89 cubic kilometer?
Yes.
Cool. So, you know, one of the important relationships is velocity equals distance d divided by time. It's the same for flux. It's volume divided by time. Cubic kilometer divided by time. Speed is meter divided by time. Okay, unit flux is square meter or square kilometer divided by time. But so I have the flux. So here I have a flux of sediment equals volume divided by time. I know volume, I know flux. What I want is time. So I need to do volume divided by flux, and this will give me time. So you take 89 cubic kilometer. How many cubic meter is this? Please express yourself. Otherwise, I feel really lonely in front of my screen.
Sorry. 89 billion.
Exactly. So 303030, and I divide by the number that
Which was about 2 million.
Yeah. So
yeah, or 3 million.
1, 2, 3, 4. So I get 25,000
years.
Yeah, if I do this equation with the high number by given by Amanda with 0.58, I guess 25. What unit is this? I feel lonely.
It would be like 25,000 years.
Exactly. Yeah. Exactly. So we have 25 kilo years to fill Lake Geneva at that rate. So in 25,000 years, Lake Geneva would be, you know, this is a view from the southeast, and you're looking at Lake, I don't know if you see my screen, you're looking at Lake Geneva, and you're looking there in the distance is Geneva. And so this lake, there will be a shoreline moving to this direction and progressively filling up Lake Geneva, like a huge delta filling this up. We can see the delta. No, we don't really see the delta on those pictures. But so the delta is here, and in 25,000 years, it will progress, make land, and finally fill up the lake. So this is if all the sediment really finally come here. You know, this is assuming the erosion rate remains the same, etc., etc. But okay, that gives you a bit of a, so in terms of buffer, it's quite important. It means there's no sediment, you know, and there are chances that there will be more climate perturbations in the future. So to answer the question you were asking yesterday, Amanda, about the real role of these kind of lakes in buffering sediment supply to downstream, you know, the Rhône Delta in Marseille doesn't feel anything coming from the valley in terms of sediments. Okay, we have to also kind of, this is a lake which is quite deep. In fact, be careful, there are some things that may cross. For instance, if the lake was shallower, and some of the, maybe some of the, in other lakes, some of the suspended load, clays, for instance, might still cross. In Lake Geneva, the lake is so big, 70 kilometers, that most of the clays, even though they are transported at the surface, they fall out and they end up in the middle of the lake before coming out here. So if you are really in Geneva here and you look at the Rhône coming out of the lake, it's pretty clean. So this is a nice water cleaner for the Rhône. But ions, for instance, in solution, they make it. Okay, so the waters, and that's important because the waters that we measure in Marseille, their composition, for instance, in oxygen isotopes, in carbon isotopes, their composition is actually reflecting the whole of the catchment. Okay, so if we had paleosoil nodules that several of you might look at, paleosoil nodules coming out in Marseille might actually be influenced by the precipitation in valleys. Okay, sorry for this longer session. I propose another break, 12 minutes, if that's okay. Like this, we start around at 11:30.
Okay.
Okay, merci beaucoup.
So I was just thinking of what you just presented. And so if there was a large increase in precipitation in the Alps, then we would, I guess, be looking at sediment within Lake Geneva to try to record that signal. But if there is a transfer all the way to the ocean, would you be able to, I guess you'd have to maybe perhaps use an isotopic analysis to try to analyze if any of those sediments transfer all the way to the ocean, or if they're all captured within Lake Geneva?
Well, I think what we just did now tells us that because even with 1 millimeter per year, I mean, it depends, you know, that's something really important. Let's say you're speaking about perturbation of climate, right?
Yes, yeah.
So let's say you have, I will say like this, it's not correct, but an increase in climate. An increase in climate for me will be an increase in the erosional efficiency of climate. Let's say you go to a more humid and erosive climate. This would increase sediment supply, okay? So this will decrease the filling time of Lake Geneva. So let's say you go, instead of 0.58, you go to 1 millimeter, that will already decrease it to not 25, but half, so 12,000 years. So if you will go in an extreme change and go to 2 or 3 millimeter, you could perhaps fill Lake Geneva in 5,000 years or 3,000 years. In that case, you know, if the climate perturbation would last long enough, then you will fill Lake Geneva and transfer some sediment to the Rhône river system in the marine basin. But you realize you would only see a fraction of what really happened, because most of it will be, the best place to look at this perturbation would actually be Lake Geneva. Down in the Rhône system, we wouldn't see much. To really see the impact of the perturbation, I think you would really need to have a big perturbation and long enough in time. So it's really possible that this lake acts as a filter for such a perturbation. Now the other way will be a decrease in climate. A decrease in climate will be dramatic, because a decrease in climate, you will lower the erosion rate. Therefore, you will increase the time to fill Lake Geneva. It's already 25,000 years. So basically in Marseille, you don't see anything when climate becomes less erosive. You only see less sediment coming in, but nothing comes out of Lake Geneva anyway. So the only way you would see those climatic perturbations will be in the isotopes. That's why the isotopes are such a great record, and they are global often because they mix quite well in the ocean. if you look at marine sections, but also if you look at continents. As I said, the water in the whole catchment is going to be affected. So I think some of those perturbations are filtered. If you look, they are not filtered if you look at isotopes, and they are filtered if you look at sediment supply.
Thank you. That really answers my question.
Okay. Let me just call Cécile. I would like. Ah, ça a l'air de marcher. Merci Cécile. Ok, share screen. Desktop. Okay, so this was first slide. Huh? It took us a lot of time. I will go quite fast. Here, this is very simple, but here I just want to come back a little bit on the principle of the transfer system. And so I try to represent a transfer system like this. It's mostly a river with a floodplain. And what are the different aspects I can speak about? I can think about it as many other systems in terms of input and output. And as a matter of fact, sorry, I'm already coming back on the first slide, but here my input is rock uplift. Rock uplift brings rocks up, and erosion weather these rocks that go up and brings them down to the outlet. Okay, so in and out. Okay, the out here is the in into the transfer or sink. So this QS in is what comes from upstream. Okay, it comes here and then it goes downstream. The question is, how much is stored, how much is trapped in this transfer system? And this could be a lake, okay? And so when you ask this question, you necessarily speak about some sort of volume or area and subsidence, or just a volume to fill, like we did for Lake Geneva. In Lake Geneva, there is no subsidence. Lake Geneva is not a sedimentary basin. Okay, there is no perennial subsidence in Lake Geneva. Every 20,000 years, it's carved again by a glacier. Okay, so this is not a basin. It's just a temporary sink for sediment because it's a hole that can be filled. But in general, on the long term, like for instance, what Philemon showed this morning, this big sediment routing system in the Pyrenees, along the way, in the drainage system, you have subsidence. And so every year you trap a few grains at the surface and some continue downstream. But this trapping every year of a few grain makes large, thick sedimentary series on the long term. Again, think about the units. Millimeter per year makes kilometer per million year. Okay, so you only need on this surface here, where you can walk. Okay, on this surface, you only need to trap a layer of 1 millimeter every year, which is 1 grain of sand every year. Over the whole surface, you trap a grain of sand of 1 millimeter diameter, and this will make 1 kilometer thick succession in 1 million year, which is actually not a low sedimentation rate. 1 millimeter per year is not a low sedimentation rate. In the Pyrenees, it's more like 0.2, 0.5 millimeter per year. Okay, so here I just think it's important when we speak about the transfer zone, flux in, flux out, storage. So flux out is flux in minus the storage, which is area. It's not a drainage area here, it's just the area that I can define of my basin, width and length, multiplied by subsidence. So the volume here is area multiplied by subsidence. And the transfer area is width times length. Alex, for instance, has had a student working in the Pyrenees, and they've done that a lot. They characterized the width and length of their sediment routing system where it was sedimenting. They characterize subsidence, and they characterize the fluxes in and out of this system. Okay, here I wanted to go quite fast, but this storage in the transfer system can happen at very different time scales, as we've already seen. And I'm not going to go long here. I just wanted to highlight this PhD of Stefanie Stoffelde, who did a PhD actually in Potsdam and Berlin, I think, but maybe mostly Potsdam. And she has a paper in eSurf in Copernicus. And she worked on how less than 1 million year duration perturbations drive the generation of terraces and how all of this is working. We are also working on this a lot in Geneva. Also, I can only advise you to get the PhD thesis of others. I mean, you can look at our PhD thesis if you want to have a look at how it was 20 years ago. But you can also look at recent PhD thesis, and the one of Stefanie, for instance, who was working. Sorry, I forgot the name, but. So the one of Stefanie is really a nice PhD thesis. You can see how she structured the chapters, how she posed the questions, how she did the state of the art. And so for you, it's perhaps important to have this idea of where you're going. You know, I often think about this analogy with people who do sculptures into wood. They do not completely discover what they sculpt when they sculpt. They often have a whole study before of where they want to end up after sculpting. And the PhD is a little bit that, is that progressively you make yourself an idea of what will be the end product. Okay, you discover a lot of what it will be progressively. It's a long process, but I think is looking at examples is always interesting, because maybe you won't like it, and you will be able to say, okay, no, that's not how I want my PhD to be. But maybe you will like it, and it can inspire you to how to write yours. Here, so this is terraces, you know, variations of the riverbed are perturbations when you perturb the river systems with grain size, sediment supply, water discharge on less than million year time scale. There is storage also in a transfer basin on the scale of million years, like in the systems we have just seen, or when you have subsidence in the foreland, for instance, or subsidence in a dynamic topography driven or thermal subsidence driven basin on the way to a long system. And you can also have, this is impossible to understand, so I will switch to YouTube, but this little drawing I just did is when the basin becomes a source itself, when you have recycling, cannibalism, okay? So, and that's on time scales of the lifetime of a basin. So when such a basin like this one then becomes involved into the deformation zone and becomes itself a source, okay? So this is more than several X, I write X million years to say several million years, or mega annum. And here is the video I wanted to show. It's from Géosciences Montpellier. Jacques Malavieille is a structural geologist, and one of those experiments he did in the lab is actually displayed in the Natural History Museum in New York. And this is a more recent one, but you know, it's sand, layers of sand, colored sand. This block here is pooled towards the left below this wedge of sediment, and here there is a backstop, there is a wall, okay? So the sediment cannot escape to the right. There is a bit of friction at the bottom, and progressively you will see, so that's the story here at the beginning. There is sand, and there is a bit of plasticine, sorry, oops, there is a bit of plasticine. There is a bit of plasticine in the middle and glass microbits also in the middle. These are weak layers in this layer cake here, okay? And so we will see how this deforms with time. There is a lot of those on the web that are absolutely fascinating. But you see, you create folds, and the people here in the lab, they erode the folds. You know, they erode that with a vacuum cleaner, actually. So they vacuum the top to sort of maintain a slope here. And they also put sediment, new layers of sediment in the basins in between. You remember Philemon this morning speaking about a piggyback basin. And so here are piggyback basins. And as you can see, at some point, these basins also become sources, okay? And so you have a whole history of uplift, sedimentation, and erosion of formerly subsiding zones. And at the end, you have a very complex orogenic wedge with many trusts and folds and mini basins. Oops, cancel. Okay, so this is just to say that a basin itself can store sediment for several million years and then become a source. So if you're looking at the complete end of the system, you may have this effect as well. This is just the anatomy of a basin. And I just wanted to highlight like a big margin. On such big margins, the fluvial system comes in and delivers sediment. You often have a delta or several deltas, a shelf, and then you have a slope, and you end up here on the deep basin. Often it's an oceanic, if you're in an ocean, this is oceanic crust. And so the oceanic crust average depth, the ocean floor average depth is perhaps 3,000 or 4,000 meters. So you have really high water depth and you are in the basin here, you're in the deep sea, okay? And you know, I've represented some strata here. It's like a sequence strat look-like section. So all of this is a wedge of sediment because it pinches down here. Here is a more even simplified representation of a margin. You have sediment, QS in coming in the margin, and it actually pinches out in the distance. And here, QS finally becomes 0, okay? But that's the only place where QS finally becomes 0. So like Jean was saying yesterday, there is always some transfer, okay? And there can also be erosion in the basin. You know, there is a canyon here, a submarine canyon. Not all of these canyons are erosive. Some are purely constructive forms. They are pure morphological forms that are actually building up like a channel, not necessarily erosive. They can be purely aggrading, but some are erosive, okay? And so this is something you may see with Alex more than with me, but you see this little arrow here is meant to represent sedimentation. So QS in comes, and a little bit of the QS in, a little bit of sediment flux input is sedimented here. More is sedimented here, and then you still sediment there. So going down like this, if you sediment a bit progressively, you have less and less to sediment. That's why you end up with 0. And that's why you have a wedge-shaped sedimentary margin. Okay, it's just because you exhaust your sediment flux. You deposit it, so you end up with nothing to deposit at the end. And that's your final pinch out, your final, it's kind of an on-lap onto the basin floor. Okay, I think it's trivial, and for you it's probably super trivial, but I think it's super important to realize that you have sediment extraction and final pinch out on the basin floor. Okay, so QS out is not a number anymore. QS here is 0, and there is no QS out of the basin. And to me, that's the definition of the basin, is when there is no QS out. A real transfer zone, which you can define at a local scale, is a zone that actually has a QS out existing. When QS out is not a number, you are in a final, you really are in a basin. Okay. This is, I just wanted to, I just did a little summary of sequence stratigraphy, because these are the elements of the basin that are important to look at. And I try to sketch everything on one single slide, and this is why I just thought about just as an anecdote, just to show you. I don't know if any of you knew or no, but when I was small, I was fascinated by this disk that the Americans and the NASA sent in space with Voyager. I don't remember which Voyager probe this is, but they made this golden disk. It's called the Golden Record. It's a golden disk with some signs on it. So for instance, this is meant to represent our solar system and where it is in the galaxy. There are instructions on how to read this compact disk made of gold, instructions on the duration, instructions on how it works, which phase has what. There is video on it, and so it's kind of our message in a bottle to the aliens. And I find it fascinating that they even did that. I think it's super, very, very cool. But also, just to say that sometimes, I mean, it should normally be able. Honestly, I don't understand any of those diagrams like this, so I hope the aliens are clever. But I think it's often very useful to try to sketch things out. It's really useful for you in the first place, and try to sketch them in some sort of really understandable way. So here, what I wanted to represent on this slide, and it reads basically from up to down. So I don't know how all of you are familiar with sequence stratigraphy, and I know Cécile will do something detailed on sequence stratigraphy. But I think you can hear it 10 times in your cursus. It will be good always. And there are many. We can have hours-long discussion about sequence stratigraphy, about its pragmatic use or not. But it's one of the parts of the science that I think is worth knowing about. And so here I put just 3 types of basins, and there are more, but this is a passive margin represented in cross section with 10 to 100 kilometers length, 1 to 15 kilometers thickness. This is a craton, a cratonic basin, so it's a basin inside a continent. And this is a foreland basin, for instance, or just a peripheral basin. When we say peripheral, we mean a basin which is around or adjacent to an orogen. So the orogen, we will discuss about this another day, but the orogen exerts a weight onto a lower plate, which makes subsidence and space for sediment out of the erosion eroded from the mountain to accumulate here. And so decades of studies have shown that we can look at these sedimentary successions and subdivide them into sequences, which are kind of building blocks. These sequences have different durations, potentially. They have different scales. But it's usually an exercise we can do when we are on the field or when we look at seismic sections. We can divide the stratigraphic record into self-consistent packages of sedimentary rocks that look like repeating with time, okay, at different resolutions. It's a bit again like Russian dolls. And these sequences also look kind of self-similar. So small sequences sometimes look, or often I would say, look like big sequences. They share common traits, common features that have been really conceptualized with sequence stratigraphy. So here I'm not into scale anymore. I'm just showing a typical marine clastic sequence and a typical continental fluvial sequence. And that's my vision of those things in my golden plate to the audience. But that perhaps can help you. And I hope Cécile, François, and during the trip in Spain, we will also discuss that in different languages. But here is a marine clastic sequence. What is really interesting in the marine clastic sequence, as it's been conceptualized by sequence stratigraphy, is that it's made of sub-packages itself, which repeat themselves, and there are key surfaces. But usually you have a low stand. So you start the sequence with a low sea level and an erosive boundary, which is called the sequence boundary. So the shelf is emerged and the sea level is somewhere here, and you deposit sediment only in the lower part of the shelf margin. Okay, and you have a landscape which is kind of this one with incised valleys on the shelf and deep sea fans here at the bottom of the slope. And there's a lot of variety there. So that's the low stand system struct. Then sea level rises and you are going to deposit transgressive systems. This is this green package here, okay? And I've put a little triangle. This is meant to represent retrogradation, landward stepping of depositional environments. And often the depositional environment during the transgressive system struct look very different from the depositional environment during the deep sea fan, during the low stand system struct. And in fact, you trap sediment here and nothing comes down, you know, you displace your final pinch out, your QS out equals 0 boundary. So everything is trapped here in a much higher situation in the landscape. So barrier island, incised valleys, etc. But no more deposits in the turbidites. That's purely theory. Huh? In nature, there are lots of variations, and we know deep sea fans that have been deposited during high stands and during transgressive systems. But I'm just speaking about the general theory. Then after rising sea level and landward stepping, we start again having progradation. The systems start again to go seaward with this downlap here. You see the downlap of this strata. So we just passed by the maximum flooding surface, which is this green dashed line. That's the maximum flooding surface in the middle of the sequence. And the blue package is the high stand system struct. And often it's made with deltas. For instance, you have deltas and you deposit slope deposits. And then sea level goes too low. We have again erosion of the shelf, and that's a new sequence starting with low stand. And I didn't draw more than that. So in terms of shoreline trajectory, you go seaward, landward, and then seaward again. That's what I represented here. Seaward, landward, and seaward again. And so that's a full sequence. Okay? The shoreline trajectory is something that was really popularized in Norway, for instance, in the Statoil and Norwegian school of sequence stratigraphy. So for me, this is really key, a key drawing to have in your mind if you want to read the stratigraphic record, because you can use that as the theory, and on the field in your seismic systems, you will find fantastic deviations to theory, but at least you have a model here. That's a model. Maybe there's not a single sequence in the world that exactly looks like this, okay? But that's how they sort of look like in general, and you can look at how your systems actually deviate. And here, this is in a continental fluvial system. So I represented channels. So here we do not look from upstream to downstream, like here. Here we have upstream, downstream. Here we look across. So the sediment flux is coming towards us or goes away from us. And so we have channels and floodplain. And often what we see is we see more amalgamated fluvial channels and then less amalgamated fluvial channels. So we can interpret that as kind of less preservation and more preservation of the sediment. That's kind of one type of building blocks. But it's true that sequence stratigraphy in fluvial environments is less easy or less evident than in marine systems. Okay, so here the system struct, I think, are super important for you because they partition spatially the reservoir properties, facies and lithologies, and not only their properties, but also the volumes. So in the low stand part of the sea level curve, you have deep sea fans with certain lithologies and sedimentary facies, and the volume is here on the margin. In the transgressive system struct, you have different types of depositional environments, and the volume is actually here on the shelf, not at the same place. Okay, so I think this is super important. Now here I define what is accommodation, water depth, sedimentation, and how to read variations of this. So this is the bottom of the basin, and accommodation is the space available for sedimentation. Okay, the space available for sedimentation is controlled by this arrow, which means that the bottom of the basin can go up or down due to tectonics. In general, in a basin, you subside. So you increase space for accommodation by subsidence, or you make accommodation space by subsidence, for instance, 1 millimeter per year. And it's modulated by sea level changes. Okay. So for instance, if your basin goes down by 1 millimeter per year and you have a sea level fall of 1 millimeter per year, you do not change accommodation with time. You remain with the same accommodation and you do not create additional space. Okay. However, if you rise sea level in addition to lowering the basin, the bottom of the basin, then you really make new accommodation space for sediment. Now into this accommodation space comes QS, which is the sediment flux, or S called often. QS comes and is deposited. Sorry. When deposition takes place, what remains is water depth. Okay. So when we look at sediments in the past, we often read sedimentation and water depth. And that's how a way to try to interpret how accommodation was evolving and especially the ratio between accommodation and sediment supply. So, for instance, if I increase accommodation, okay, but I also increase sedimentation, and both change at the same rate, my water depth will not change. That will be aggradation. If I increase accommodation faster than I can bring sediment in, okay, let's say I increase accommodation by 3 millimeters per year, and I sediment only 1 millimeter per year, then every year I add an extra 2 millimeters of water depth. So in my sediments, I'm going to see more and more deep sediments, and that will be retrogradation, deepening upward. And of course, if I increase accommodation slower than I can sediment, so if I sediment faster than I increase accommodation, I am in a progradation situation where I shallow upward in my sediment. I observe a shallowing upward succession. And so that's a symbolism that is perhaps common in some oil companies. I just want you to know it, you know, I don't insist on that, but I think it's very useful to represent shallowing upward, no change in water depth, aggradation, and deepening upward. Sorry. And so we have important boundaries into this. The sequence boundary here, which we saw here, is somewhere in the progradation. It can be at the top of the progradation if we are in the exhumation part. It can be within the progradation if we are down in the low stand system structs. And the maximum flooding surface is at the turnover time between retrogradation and progradation. You know, you can see here, low stand, transgressive system struct, backward, landward stepping, and then progradation. So we are at the turnover, the maximum flooding surface is at the turnover between retrogradation and progradation. Now, another very important diagram, which repeats a little bit what I just said, is this one. And I think, you know, all of you should have this exact picture stored as, you know, as in you store pictures in your computer or in your phone. You can store that in your mind. It's an easy, I think, picture to store. It's shoreline trajectories, the pattern of sedimentation of a shelf and slope system or a beach, for instance, beach and shore face system, and correspondence in terms of accommodation of a sediment supply ratio and the triangles. So in the situation here, what I represent is a seaward stepping of the sediment. So there is always 3 times of sedimentation, T1, T2, T3. And my shoreline, let's say this inflection point here is the shoreline. My shoreline is going seaward. To the right is the sea, to the left is the land. It's going seaward and it's also going downward. You see the arrow is actually inclined to the right. This is when you decrease accommodation. Okay, you have A over S less than 0. And this is forced regression or forced progradation. So it's within this triangle. Here you also have seaward stepping, but the shoreline remains at the same elevation. So my arrow is horizontal, flat. This is when you do not create accommodation. Okay, accommodation is a vertical dimension. Here you do not create accommodation. So imagine you do not change sea level and you do not have subsidence. Your accommodation is fixed. The only way you can put sediment is seaward, where you still have space. Okay, so you have pure progradation. This is called pure progradation when A equals 0, accommodation equals 0. Sediment supply is of course a positive number. This last progradation case is when you have seaward stepping. So in these 3 cases, we have seaward stepping. The shoreline goes towards the sea. the arrow is to the right. But in this case, we have positive accommodation. And so not only do we step sedimentation towards the sea, but also we have a component of vertical accumulation. So the composition of this vector plus vertical gives this vector. And this is when A over S is more than 0, but less than 1, because sediment supply is still greater than accommodation. And that's normal progradation. So here we have forced progradation, pure progradation, and normal progradation. Interesting end member here, super interesting end member, is when you have aggradation. Another word that is in use in geomorphology is steady state. So this is when nothing changes. Okay, your profile, there is subsidence, and your shoreline remains at the same point in space, except there is vertical accumulation. So this is a this is an end member case. In reality, it's difficult, but when you change from progradation to retrogradation, there is a moment when there is aggradation. Okay. And this is A over S equal 1, and this is meant aggradation. You know, the vertical arrow here, you can think of it as the vertical side of this rectangle. Okay, so aggradation, and again, aggradation is also steady state. Sorry, I received tons of messages. I was wondering if this was Cecilia. And now, the last case, so there is 5 cases. The last of the 5 cases is when we step landward. And when we step landward, we have the shoreline going backwards here. And this is landward stepping. This is A over S is more than 1. And this is retrogradation. Okay. This is when there is accommodation, which is faster than sediment supply. Okay, so this is my golden record about sequence stratigraphy. I think it summarizes a lot. It's not exhaustive, but I think, honestly, I think even if you do geomorphology, it's good to have this in mind.
Can I ask a question?
Yeah, sure.
Just about the ones you just described, like the last one, the propagate, this one, and the totally
vertical.
No, below, yes, this one.
Yeah.
On this schema, it seems quite similar, even if I see the difference. On the field, when we'll be there, is there a possibility to differentiate them like really clearly, like it will be the sediments composition, or will there be like really signs or something?
You mean that, sorry, my mouse doesn't, this one and this one looks similar?
Yeah, yes, it seems quite similar. If we do a schema that's a bit dirtier than this, it will be like the same.
No, so they look similar, but they are super different, because look in detail. What you see, important is time. This is time 1, time 2, and time 3.
Yes.
Okay. For instance, the last moment of deposition is lower than the previous, and you unlap here, but you go to the right. So here, this is time 1 and this is time 3.
Yes.
So basically here you have an unlap to the right, and this one, they come on top of each other, whereas this one, they come down of each other. So the geometrical relationships are actually very different, but I agree with you. If you don't, you know, this line here goes on top of this one. This is a downlap, whereas here we have a non-lap onto the former slope. So I totally agree with you that they kind of look similar, but you cannot put this below this, because this is ancient and this is new. So you cannot put ancient. Sorry, in this case, there is this time aspect into it that makes them very different.
Okay, and on the field, it will be like the sediments composition.
No, on the field, you will try to see, all of these cases. You will see, for instance, these are shallow facies and deeper facies.
Yes.
And so you will see that the deeper facies are progressively found more and more seaward. So here, for instance, on the field, I can see which strata is younger than the preceding strata.
Yeah.
So I would see that my younger strata here is more towards the basin than my preceding strata.
Okay, so we'll see like cycles.
Yeah, you will
Okay.
see like cycles. Whereas here, you will see that my younger strata are towards the proximal side of the basin more than my preceding strata.
Okay.
So on the field, this is how you would see that.
Okay.
Also on a vertical section, let's say you only have a core. Okay.
Yeah.
And you have a sample here. Do you see my mouse?
Yeah.
And you have a sample here. Okay.
Mm-hmm.
This sample is shallow facies, and this sample is deep.
Deep.
Okay, so you have a deepening upward succession. Here, you have a deep, and here you have a shallow. So here you have a shallowing upward succession.
Okay.
Okay, so it's completely reverse. This is deepening upward, and this is shallowing upward on a vertical dimension with time.
Yeah.
Okay. That's why I say it's always important to have upward.
Mm. Okay, thanks.
Okay.
Could I ask something as well?
Yes, Takis.
Very quick, just wondering. So every change in the shoreline, for example, in the forced regression stage,
yes,
wouldn't this impact the whole equilibrium profile? So meaning this would have an impact all the way from the source to the sink, and all the zones and probably parameters that we have discussed earlier, for example.
It could, but it could as a source to sinker. The question you have to ask is, will the magnitude be sufficient to have an impact all the way? And will the duration be sufficient for that perturbation to be felt? Let's just show me, I just end the show here. Let's just, I just want to show you something. Maps. Google Map. Where is Google Map? Google Maps. Let's go really wide. Okay. And let's, where is it that I can change? Menu, relief. It's really a nice one. Okay, do you all know about the Messinian salinity crisis?
No.
Yes.
Okay, how many knows?
A bit.
Okay, so the Messinian, I don't see you because I'm sharing again, but the Messinian is...
I know about it, Sebastian, but I want to see you summarize it in 2 minutes.
Okay. Messinian salinity, I write to everyone so that because it's not an easy word, salinity crisis, or MSC, is a moment in the history of the Earth about 5.9 million years ago. That's at the end of the Miocene, in the stage called the Messinian, when we think somehow connection here between the Mediterranean and the ocean was closed. When this happened, the ocean didn't give water to the Mediterranean anymore. And because of the warm climate that you know of, the holiday climate of the Mediterranean dried out. Okay? So the drying out of the Mediterranean was very abrupt and fast. So perhaps in hundreds of thousand years or less. These are subjects of debates. But basically it dried out. Sometimes water was passing. We know that because, and it's called the Messinian salinity crisis, because this was discovered when people discovered massive amounts of salt deposited. Okay. If you only dry the Mediterranean, you only make 30 meters of salt. You know, given the concentration of salt in the sea, if you just dry the Mediterranean entirely today, you will end up with 30 meters of salt. And they found kilometers, which means that periodically the connection was again working, so that you would input some water, dry, input, dry, input, dry. But it was a crisis because overall it was drier and it was, the sea level went really down. At some point you may have been able to cross by foot. Okay. So this is a massive, so that's a super interesting stage, okay, of Earth history. And we can study it with many, many aspects. But with respect to what we just discussed, when this happened, we know that the big rivers like the Rhône, maybe not the Ebro, there is debate on this, but the Nile here in Egypt, here, the Nile Delta. So the Rhône, the Nile, and other rivers around the Mediterranean, they all, you know, the sea level fall was about 1 kilometer. So you can imagine the shoreline coming here, and there was a huge perturbation of the longitudinal profile of the river. And those rivers, they started to actually incise. And you had a huge canyon here, like a Colorado type canyon here in this area, maybe 1 kilometer deep. So what you said is very true. In this case, you perturb completely the river profile, and you may have incision that propagates. But what we know is that this incision during the Mediterranean didn't propagate all the way here to Switzerland, for instance. It propagated very highly up into Lyon, okay, but not all the way into the Alps in this area, as far as we know. So this means that it didn't have time, because at some point the connection was made again and the Mediterranean refilled, and you actually filled those valleys with sediment. Sorry. So the timing, the duration of the perturbation and its amplitude are important in terms of propagation of the perturbation. You know, it's a very good point you brought up, because that's exactly on topic for the whole ITN source to sink future project. Now imagine the Messinian salinity crisis, or just the sea level fall and the drying of the Mediterranean. Imagine it takes place tonight at 11 o'clock, but tomorrow morning at 6 o'clock, you refill the Mediterranean. Okay? Unless you're having a party on the port of Marseille, if we are here in Geneva, we don't see anything of this. Okay? It's a dramatic sea level fall with immensely high rates of sea level fall, 1 kilometer or 2 in a night, but equally immense sea level rise right after, and there is no time for erosion to take place. So as huge might be the magnitude of this event, you know, completely imaginary event of a sea level fall and rise overnight, if you don't give it time to manifest itself, if you don't give time for erosion, it will not propagate and we will not feel anything. This won't be felt. Okay, so all of these perturbations of sedimentary systems are signals, and signals are always characterized by magnitude, amplitude, and duration. The rate is not enough, because the rate, the speed of a process is important, but is not enough if you don't give time for that rate to make an effect on the surface of the Earth. Did I somehow answer your question?
Absolutely. Thank you very much.
Okay, Takis. Okay, I would like to this slide is divided in two by this green one. The upper part is more uplift, subsidence, erosion, and the lower part is more, the upper part is more uplift and erosion, and the lower part is more subsidence and deposition. So I just, I think a lot of the source to think approach, as I explained yesterday in the history, owes its value to the fact that it really unites the geomorphological community with the sedimentology or sedimentary geology community. And so, you know, some of the concepts are really equivalent. It's just the sign on them which is different. So uplift is a vertical motion of rock up, and that's what dominates in a way geomorphology, because of course you do geomorphology in mostly erosional landscapes where there is uplift, whereas sedimentology is made in areas where there is subsidence, which is the vertical motion of rocks, but down. But so uplift and subsidence are really similar concept. It's vertical motion of rocks, except the sign is different. And erosion and deposition are also two very similar concepts, except for their sign. But a lot of the reasoning are similar in geomorphology and in sedimentary geology. And perhaps for the sake of this afternoon's lecture by Jean, I will perhaps only speak about that part, and maybe later or when I give it to you, but we can speak about this part below. So here I want to define some terms, but again, Alex, Jean, François, Miguel, please intervene if you see subtleties that I'm missing here. But I think, you know, this is a little sketch with a variable which is U, minus another little sketch with a variable which is E, erosion, equals another little sketch with dz over dt. And in general, dz over dt, z is elevation. So elevation is a perfect number to characterize the surface of the Earth. Is at what elevation is it? So, and that's z. When we speak about, for instance, landscape evolution, it means we are interested in how the elevation evolves with time. And dz over dt is simply the change in elevation over a certain interval of time. So when we speak about uplift of the European Alps, you know, like in the GPS paper of Pietro Sternai that I showed you yesterday, basically is looking at how the elevation of the Alps is evolving over time, and we find 1 or 2 millimeters, that's dz, per year, that's dt. Okay, it's a rate, it's a velocity of evolution of the surface. And here I wrote surface uplift. If it's uplift, it's positive, it goes up. It could be surface downwearing. Okay, the surface could also be going down. But that's just how the surface varies. And how the surface in a mountain range, in an erosion zone evolves is the result of uplift of rocks, U. So I represented here, you know, the normal surface, and here is a a mountain in equilibrium on the mantle. That's rock, and uplift is pushing this block upwards. So the tectonic forces push crustal and lithospheric rocks upward. Okay, so you can measure and say the rocks are going up at a certain speed, u. On top of that, you have erosion, okay, which is a number also in millimeter per year, for instance, that corresponds to erosion. That corresponds to going to degrading of the surface. That's also exhumation. So if I do 1 kilometer in 1 million years of erosion, I degrade, I dig 1 kilometer in 1 million years. I dig out 1 kilometer, okay? And the result of these two is surface uplift. So let's say I have 1 millimeter of uplift of rock per year. The rocks are pushed from an engine which is below, you know, in the depth. I push 1 millimeter up per year. If I erode 1 millimeter up per year, my dz over dt is u minus e is 0. So if my mountain goes up 1 millimeter and I erode 1 millimeter per year, I see no change in landscape in my landscape. Okay, my form, my geometry, the elevation of the surface is the same. So it's very important, because in such a state that will be a steady state, that's called steady state, u equals e, when uplift equals erosion, you have dz over dt equals 0. Very important, because you can have your mountain range there in the landscape. Let's say you live 20 million years and you're old enough to watch it evolve. You don't see it changing from the distance. You don't see anything. But the rocks at the surface after 20 million years are very different than the rocks that were there at the beginning of the mountain range, because they've been exhumed. Okay, they've been pushed by uplift and there's been erosion. So at the beginning, you have a sedimentary cover. At the end, you have granitic, gneissic, and you see the basement of the mountain range. So you can have a perfectly non-evolving landscape. That's a steady state landscape, yet there is uplift and erosion on it. That's when u equals e and dz over dt equals 0. I symbolize this in an orogen. That's a drawing I remade from a paper by Sean Willett. And you see I put a little vector up in black, which is uplift. And in this, these are the particles, these are the path of the particles. When I have a plate coming here, a bit like in the experiment I showed you before by people from Montpellier, Jacques Malavieille. The rocks come from the left, goes to the right. They hit a backstop. UP is upper plate, LP is lower plate. This plate goes down. And the rocks are scraped off here in an orogenic wedge. And this is the particle of rocks. And uplift is the little arrow here up, and there is erosion in blue, the little arrow down. The two are the same, or in red. The two are the same, so this whole shape can be absolutely preserved. Okay, and there is an erosion flux, which is all this big arrow going to the left, and erosional flux going to the right. Okay, to have topographic growth, meaning to have a mountain range growing, you need uplift more than erosion. Okay, and then dz over dt is more than 0. So every mountain range goes from a state which is first uplift more than erosion. At some point, the two might be in equilibrium. That's, you know, in the Davis concept. That's when the mountain range is some sort of maturity. It's a concept that draws from human maturity. It has nothing. A mountain range is not mature. It's just that you reach a state where uplift and erosion are equal. And then at the end, uplift will eventually diminish, and erosion will take over, and will downgrade the mountain range back to an elevation of 0. Eventually, maybe after a long time. And so it's interesting to study this and to have these concepts in mind. Is this okay? I think steady state is one of the most important concepts. Whether it exists in nature is a whole different story, but we don't even have to worry about this yet. You know, a concept is interesting and valuable if it's useful. And we can study deviations to steady state. We can have steady state as a starting point for experiments. It's an interesting state. It's an.
I have a. Sorry,
Yes.
I have a question. If I don't know how to say that, the steady state, is there a notion of time over which it has, well, we consider it as steady state? I'm thinking about the Pyrenees and between Paleocene and Eocene, when you have the activity of the mountain range that is not really high at this period.
Mm-hmm.
Is it steady state or?
It's a good question. Here, you know, there is a DT, so there is a time scale. Okay, the question can be studied perhaps in two aspects. Over how much time do we need to reach eventually steady state, and then how long can the steady state be maintained? And that's one. And there's a paper by Kelly Whipple actually in 2001, which the title is "How Plausible is Steady State?" Not possible, but plausible. Steady state is possible, but how plausible is it in nature? And so he looks at real dimensions of uplift, real dimension of erosion, etc. And the other question is at what scale? Here I only speak about mountain scale dz over dt. You know, if I'm looking with my glasses of 1 million year time scale or like I was saying before, let's say I can live 20 million years. I look at this mountain range such as a little thing that I can look at evolving over 20 million years. If I zoom in, I will see a landslide taking a lot of erosion at one place in one event. So at a small spatial scale, at the scale of hill slopes, at the scale of rivers, at small scale, you're never at steady state. Okay, you're always you're always oscillating between a lot of erosion and an uplift, and then a lot of erosion and an uplift. But overall, the two average each other and are in some sort of long-term equilibrium. Okay, so that's the spatial scale, and for the time scale it takes to reach steady state. That's something we can study with models. You impose uplift in a mountain range. Progressively, a landscape will develop. At the beginning, the slopes are small, and the erosional capacity is not very high. But progressively, as elevation increases, the slope also increases. And provided you do not change climate, you will at some point reach slopes that are sufficiently high for water to transport sediment in a sufficiently efficient way, such that erosion becomes equal to uplift. Then what Whipple says, for instance, is that the time scale to reach such equilibrium is anything between 250,000 years to 2.5 million years. But so these are kind of million years time scale. But if you look at climate cycles, 20, 40, 100,000 years, climate cycles are modifying the erosional capacity. They are modifying the E vector on timescales that are quite short. Okay, so potentially, if you look with those glasses, if you look at the 20,000 years or 40,000 years timescale, a mountain range is never really at equilibrium. It's downgrading a bit faster during more erosional climate, and then it's eroding a little less fast, a little slower during less erosive times. So in the Pyrenees, when you speak about the Paleocene, there is a moment where we think actually tectonics was a little slower, at least convergence rate. I'm not sure that's the case or not, but I take it from literature. And in that time, actually, I'm not sure we know if the mountain was already at steady state. Also, a mountain can be at steady state in one place and growing in another place. If the collision is oblique, like Taiwan, for instance, your mountain range can be in a steady state in the part that has been colliding early and that has had time to reach steady state, and at its tip, where collision just starts, it's still growing. So these are concepts that need to be declined and looked at in detail for each specific case in a way. But they are an interesting concept to as a kind of an anchor, if you want, a conceptual anchor. Am I far from steady state? Am I in the growing stage towards steady state? Am I completely out of steady state or close to steady state? These are I think the important questions.
Sebastian?
Yes.
If I can also add something, I think it's also important to consider the isostatic rebound that constant erosion might cause in mountain ranges.
Absolutely.
Right? Yeah, because and then this could trigger a possible positive feedback, but so
yes,
it's hard to conceive that a mountain range can never reach a steady state.
No, I think they can reach some steady state. But so the erosional, so you know, U and E here is very good what you say, are not in what comes out of this discussion, both what Marine asked and what you're saying, Everton. Out of that, what I would take is that U and E equals dz over dt, but U and E are actually not independent of each other completely. Okay, they are to some extent independent, but not to some extent, not completely. Because as you said, erosion takes rocks off, and by taking rock off, it triggers an isostatic response. And uplift, by bringing rocks up, increases the slopes. You know, this is a drawing where everything is square, but in reality, you have slopes. And by increasing the slopes, uplift increases erosion. So these two variables are actually dependent on each other, and that's the whole difficulty, and that's why it requires modeling. I think you know, U minus E equal dz over dt requires to put that in a model that will help you assess the role of each of those factors in going to steady state or going out of steady state. You know. Can you make a mountain grow just with erosion? Okay, or can you? Is it sufficient to stop uplift to downwear a mountain range? These are questions that just with U minus E equals dz over dt are difficult to solve.
Yeah.
Okay, we can make the same reasoning for deposition, but this will be dz over dt. Here, I think will be the aggradation, retrogradation, and progradation. But we can do that another time, because I would like to switch to this slide. And here I'm also not gonna speak about everything, but it's a slide which is not finished, obviously. But I took a little bit. I was drawing, you know, a little bit the same as I did before, and in the source slide of this morning. And so what you see is one drainage basin, another one here, and here is half of one with a concave longitudinal profile. This morning I said this is the drainage area, of course, with the outlet here. Of course, if you go up the river, you walk up the river and you come here, you can also measure discharge here, okay, up the river. And it's going to be smaller than the discharge down there, because down there the drainage area is bigger. Here the drainage area is just the drainage area that I have above myself at that point, okay? And this can be measured with DEMs and flow routing algorithms, which is just algorithms that calculate how much surface is drained above a certain point in a longitudinal river profile. I can measure that in real landscapes. And as you can see, drainage area can be seen as increasing downstream. That's why a little a middle A, and a big A. So as I walk downstream the river, the drainage area above me increases. So this is also here, but it's just a half view of the basin. So as I walk down, drainage area increase. And if I only have a longitudinal profile, I only know the distance I'm covering. L, small l, middle L, big L. So the distance from myself to the head of the river. So as I walk down with L, the drainage area increase, and it increases. We can think about it as increasing as a function. Drainage area increases as a function of L according to Hack's law that we have seen this morning. Okay, there is a relationship, L equals 1.7 times A times drainage area, square root of drainage area. In such a bedrock river profile, and so here is Z, the elevation. We can, there are different things, and Jean will speak about that a lot, but we can define, let's do it like this. We can define or Alex could also explain this very well, and perhaps he will do it also differently, which will be good for you. But the stream power, the power of the stream is, if you zoom in here, that's a zoom of a little piece of the river. There is the riverbed with a certain slope, the water surface with the same slope. Usually we don't see it, but it does have a slope. And the water is flowing with a certain velocity. And because it has a certain way here, it exerts a force on the bottom of the stream. And that's or a stress on the bottom of the stream. And it's often seen as a shear stress. So it's a stress that shears that shears at the bottom of the river. My mouse is blocked, simply because the profile of the river velocity is high here and very small, down to 0 at the surface. And so you exert a shear, exactly like if you press on the table in front of you with your hand and move your hand, you're exerting a shear. If it was a soft tissue in front of you with your hand, you would shear the tissue, okay, or a piece of paper. And so that's what is responsible for the motion of gravel and of sediment at the bottom, with a different range of processes, like grains rolling, grains jumping around, and some of the smallest grain, they are even transported in suspension when they are detached from the ground. But all of these processes integrated, they result into some erosion. Okay, the erosion, that is dz over dt. And there's a whole range of studies which are interested in trying to understand how erosion is linked with all these processes and all the forces, the mechanical processes, the abrasion, the plucking, how little grains come and hit the ground and take off pieces of the bedrock, how grains transform, how all of these processes act, you know. Also the distribution of flooding events, the differences in water depth, etc. But all integrated, it seems that we can think about this, the power of the river, the force that the river exerts, and its erosive power is proportional to this equation, which is K, some sort of constant of lithology of climate, A, drainage area to an exponent, M, and slope, sorry for S, because we often have it as sediment supply or sedimentation, but it's also slope in geomorphology. It's the S which is here. So to an exponent. A is drainage area. So why is drainage area in this equation? Because drainage area, as we've seen before, is given a certain amount of precipitation. Drainage area gives you the discharge. So for assuming, not discussing about precipitation, a river which has a bigger drainage area than another one, and the same slope, the same lithology, if it has a bigger drainage area, its stream power will be bigger because it has more water. If the slope increases, the stream power will also be bigger because the water flows faster. Okay, and there are exponents here that are, I think, both theoretical and empirical, but we shouldn't go too much into this, or I will leave Alex and Jean to talk about them. But even if we set them both to 1, it still works. Bigger rivers are more erosive, everything else being equal, and steeper rivers are also more erosive, everything else being equal. Okay, this just makes sense, I think. So here in such a river which is flowing on bedrock, what limits is an ambiguous word, but what limits here means what controls the evolution of the river profile is its capacity to erode. Okay, and that's why we call it detachment limited or erosion limited, but detachment is its capacity to detach new particles from the bedrock. Okay, so let's assume a constant uplift. You look at a river, this river has a clean bed, it's bedrock. The evolution with time of the elevation of this riverbed is modulated by erosion if uplift is constant. So that's a detachment limited river profile. Okay, it's very small. I hope you have bigger screens than me. But so in this case, erosion is proportional to K, AM, Sn, and that's dz over dt. Detachment limited bed evolution. That's number 1. Number 2 is we have, I already spoke about this, an aggregative drainage basin. This is typical of the source area. It's not completely typical of this area, the alluvial basin, because over long stretches of the alluvial basin, you can have no aggregation of new water. So you can have river segments in the alluvial domain that over which long stretches of rivers over which the discharge does not increase as you go downstream. At some point, the river, they merge and suddenly it increases. But you can have long stretches with no increasing drainage area, whereas this is not the case in the bedrock in the source area. As you go down, the area increases. So I wrote a big A with little a's here, increases downstream according to Hack's law. L proportional to B, A, C. B this morning we saw was 1.7 and C, the exponent, is 0.5. So we can write A equals L square divided by square of 1.7, which is 3. So A equals L square divided by 3, basically, if you want to write A as a function of distance along the river, this distance here. Now I want you to study the case of a steady state river profile. So here I would like to switch to stop share. And now share. I think you can all click on share and you can all click on whiteboard. Can you do that?
Yeah.
So I don't know how this works, but let me see. Do you all have a whiteboard or no? So only one participant can share, or I'm not sure how this works. Or do you see?
Yeah, I think I'm not sure we can all write on the board, Sebastian. I think you should be the one.
Okay.
Creating just your whiteboard, and whatever you write, we all see it instead of your screen.
Okay. Well, then take a piece of paper. That's a small, a little exercise I would like you to do. Take a piece of paper and let's do that. Let's do an axis like this, which will be Z, elevation. I can select that, put it here perhaps. Let's make it clean. Oops. Then I draw another axis here. Excellent. And I put text, and here I put X, and that's distance downstream along my river. Let's say here is the outlet. And let's say here is the source. Or head, channel head, river head. Okay, now the exercise is how do you draw? What will be the shape of a river profile going from source to outlet?
Be concave, right?
Concave.
Yeah.
Okay. So I don't think I have a concave. I'm gonna have to draw something like that. This is not gonna be nice. Ooh. Is this linear or concave? Wait a second.
That's how we find river profiles in nature, right? It's never perfect.
That's true. Thank you for your support.
No problem.
I try to do maybe something a little more concave. Okay. Okay, that's a concave longitudinal profile. Thank you, Everton. There's a few nick points and a few pools and riffles on the way. So now what I can draw is the uplift vector. So this is uplift. Uplift U. And that's in maybe in millimeter per year. And that's U in millimeter per year. And so can I do that? Make a copy from say from there. Okay. Can I not just copy this? No. Oh, well, that's a pity, but let's maybe try to do it again. You know, I imagine that I'm in a mountain range where uplift is, I'm looking at this section I was looking at before. Uplift is the same everywhere. So everywhere my rocks are pushing from below at the same rate along this river. Okay, so that's the, you know, the uplift is like that. Actually, I should grab them, and in fact I should put them here. The surface of this river is pushed up like that. Okay. So how do you draw in your little drawing the erosion arrow to have this longitudinal profile being at steady state? It's a trivial question, huh? Okay. So I think
it has to be the same.
Yeah, it has to be the same.
But in the other direction.
But in the other direction.
To
exactly.
the bottom.
So I chose red, and I will put it here. Okay. Equivalent. Let's do it like this. So that's erosion, such that I am at steady state. Oops, I cannot modify U. Oh, yeah. U equals constant, and U is uniform, means U is the same everywhere. Okay, in this mountain range. And E, erosion, or let's say big E, equals erosion, is also constant and uniform. Okay, so that's my steady state situation where U minus E equals 0, or let's say dz over dt equals U minus E, and I find that it's equal 0 because both vectors are the same. Now I just want to highlight the fact that let's think now about erosion. So the E, the red vector, erosion we just said is, let's say is equal to K times A exponent M, but I will say exponent 1. Do you understand if I do this times A times slope? Okay. This is the stream power law.
Okay.
but stream power law with m equals n equals 1. It also works with different exponents, but I just want, for the sake of this explanation, I just want to keep them equal to 1. Do you all follow until here?
Yes.
Okay. So I just want to highlight that the stream power law now explains why the river profile is concave. Okay, I don't know who said that those concave profiles are what we found in nature, but they are typically what we find in nature, because if erosion is constant, okay, if this vector here is the same as here, what is not the same at this point and at this point? What is different in both locations?
Slope.
The water speed, the discharge.
The discharge and the drainage area. Is the drainage area bigger here or smaller here than here?
It's bigger.
It's bigger.
Bigger in the outlet.
It's much bigger, okay? So to have the same erosion, what do you need if drainage area is bigger? You need to have a proportionally smaller slope. You know, as drainage area increases downstream, if you don't do anything to the slope, your erosion will increase downstream. So as drainage area increases downstream, slope decreases proportionally to keep erosion constant. And that's why you have a concave longitudinal profile in this type of setting. I know this is fully theoretical, okay, but this is what explains why you have a concave longitudinal profile, and I think it's major, okay, because it's a major observation, and it's also potentially a confirmation that the stream power law actually works quite well and is a good description, at least, of what we see in nature.
Yeah. Seb, I think it's worth pointing out that the downstream distance x is well understood and is proportional to the drainage area. In fact, that downstream increasing distance scales with drainage area in a predictable way.
Yeah. So x equal as a.
A goes as x squared, basically.
Yeah, A scales with L square. Okay, this is from Hack's law that we've seen before. Okay, so drainage area A equals as a function of x. Okay, is the distance, so it's actually x squared. Okay, so as x is increasing here from 0 at the source to 20 kilometers, drainage area increases, and erosion is a function of x, okay, and it increases with drainage area, but at steady state, to keep erosion constant, my river profile will have its slope decreasing, and therefore we have a concave longitudinal profile. Okay, now let's move a little bit the things here. Okay, so that's a set of things, the first set of kind of results or points. Now, you can, that's also Alex's turf, but you can also write that you know, we said we are at steady state, therefore U equals it actually equals to erosion. So it's actually equals to K times A times S, right? So the slope, we can pull out the slope from there. Oops, how do I do that? Because the slope is something we can measure. So can I do that? How do I do that? Slope divided by K. Is that correct? U divided by K times A. So this, you can, with the evolution of how slope increases downstream, and we will go there to something called the steepness index. With the evolution of the slope downstream, and because the slope, you could have a small evolution of the slope if I had a drawing, a concave profile, but much less concave, or you could have a very concave profile. How this concavity is, or how steep is my profile. It's actually an index of steepness. How this changes with distance is a function of uplift and the relationship with drainage area. So there is also the climate and the lithology can be into that. But many studies have used the shape of those river profiles to, assuming with certain assumptions in the background, to derive uplift. Okay. So that's, I think, something you will, I don't know if you will do that with FastScape, but you can at least test this. And that's something I wrote. I mean, now I'm sharing. Do you see only the whiteboard, or do you see also my PowerPoint?
No, we just see the whiteboard.
Ah, okay, okay. Ta-dam. Stop share. Share. Desktop. So, you know, that's the little steady state here that I wrote. So the slope, which is dz over dx, decreases with, so here I kept the exponent, for instance, but that's really a relationship between erodibility. Sorry, I never said that, but K is the erodibility, and the ratio between erodibility and uplift. Okay, modulo climate always, but I think that's a very important realization, and it's been complexified a lot. So you can look at papers on that, but this was for a moment, you know, in the years from 1999 to maybe 2006. Can you mute everyone, Cecilia, or Melanie at least? So I think between 1999 and 2006, I remember there was 2 or 3 papers every month with steepness index, and here is how we found that there is a new thrust in the Himalaya, because we've looked at river profiles and assumed the uplift was uniform. So there is a lot of literature on this in those times, and it's been an incredible